So since this meeting is already pretty old, means already a couple of days has been spent and many people have told, so I assume that all the faculty members who are attending this meeting, they're now become familiar with the language in which we speak. So the words like bra, K, Ketsai, or quantum gates, or say entanglement, those are now by now familiar word. And but still I'll give some introduction, and I told that I'll talk on introduction to different aspects of cryptography and hacking uh, in the post-quantum world. So you see, I did not say that quantum cryptography. So what is post-quantum world? By post-quantum world, we mean a place where there are scalable quantum computers. So where are we now? So we on and off we listen that there is a quantum computer, but those quantum computers are very small and they are noisy. So we say that they are noisy intermediate scale quantum computer. So at the moment we are in a NISQ era, noisy intermediate scale quantum era, and eventually we may go to a fault tolerant era and we have a scalable quantum computer. And many things will change at that time. Not only the job of people like me or you, the job of police or CBI officer may also change. So I'll come back to that. So before that, I would like to request all the participants who are attending online, they may take a screenshot. I have shared my email ID, and so in future also, if you have a query which you could not ask now, means you can drop me a mail and ask your questions. So now, in the left hand side, I show two pictures. The lower left picture is of Professor ECG Sudarshan, and the next one is Glauber. So why are they here? So we don't discuss much about them in a quantum computing or quantum cryptography course, but they define the notion of non-classicality. So there is something called Glauber-Sudarshan P function. If P function is negative, we call the state to be non-classical. So without defining P function, I just want to tell you that a non-classical state or non-classical property means something which does not have a classical analog. So if you need any quantum advantage, you must have some kind of non-classicality. If everything has a classical analog, then you can do that in classically also. So non-classicality is very essential for obtaining any kind of quantum advantage. Now, in the right, I show a person named Dirac. So he provided the framework for second quantization or field quantization. So many of you may be familiar with the Dirac equations or the basic backbone of relativistic quantum mechanics, but these people played a very crucial role on the kind of things which we do, because we do whatever we do, the photon is essential for that. So I do quantum cryptography, I do quantum computing with photons, photonic quantum computing. So there are other ways to realize qubit, but in all our work, photon play a crucial role. Now you look at this picture. So FDPs and workshops like this are organized for interaction. But now we are talking about matter field interaction. So this is light and this is matter. So after so many years of interaction, I don't understand you. So light is saying, for a better understanding, you have to be quantized, as our relationship is quantum optical. So that's very interesting cartoon, and we need to quantize the field to understand things better. So this will be clearer as we move on with the presentation. So where I do all these activities, we are located at Noida, somewhere near Delhi, and here I have a lab where we do quantum cryptography. So in this lab, in cryptography, always the information is sent from Alice and receiver is called Bob. So sender is Alice, receiver is Bob, and they are separated and they want to distribute a key, a secure key, and then it is called quantum key distribution when quantum resources are used. So one you see in the right hand top, this picture is of a QKD setup. It's called coherent one-way or cow protocol of QKD. So here there is you can see some wooden boxes. So each of these boxes have 20 kilometer of fiber spool, two such a spool. So each box contains 40 kilometer of fiber, and I have 120 kilometer of optical fiber in my lab. And Alice and Bob are sitting in the same table, but they are separated by, I can separate them by 120 kilometer of optical fiber. So we do quantum key distribution over such distance, but distance is not the main crucial point. More important point is how much noise over this channel. So normally these optical fibers give a loss of 0.2 dB per kilometer. But in practical, say C dot implemented made this setup in collaboration with us, and then CDOT went to implement it in the real situation, and then they find that even a 16-kilometer laid down fiber has a 16 dB loss. So 1 kilometer is causing 1 dB loss. So in the lab, which was good for 80 kilometer, that much loss is found in the 16-kilometer real life fiber. So these are concerns, and there are many technological applications. But beyond that, we'll come back to challenges. We'll come back to hacking ideas. So hacking is the art of cracking the code to know the secret. Now, who are interested in it? So since it is organized in Odisha, which is very close to West Bengal, and the language is also very close, so I start with Tagore's a few lines from a story called Guptadhan, so hidden treasure. Paye dhore shadha, ra nahi deয় radha. Sheshe dilo ra, so that means Radha has ra and dha. So ra nahi de, he was not giving ra, but she gave dha, and at the end she gives ra. So what we have is dhara. Then pagol charopa means pagol. Let's leave pa. So what you left with is goal. So it becomes dhara goal. So dhara goal is the place where you have to go. Tetul water kole dokkhine jao chole. So you see, Tagore was also somehow attracted to cryptography. So he is encouraging here to decode a message. So what is the encoded message here? The encoded message is there is a place called Dharagol where you can find out the hidden treasure. For that, you have to go from a particular tree south of a particular tree. So not only Tagore, Edgar Allan Poe was also interested in cryptography, and there is a story called The Gold Bug. It contains the famous cryptogram which helped to spread public interest in secret writing, detective stories, and even inspired modern cryptologists. So even if you are not so much in cryptography, you can understand that, and this is something which you use every day. Every time you are giving a OTP, every time you are making a transactions, every time you are making a UPI payment, cryptography is some way or other used. Now, cryptography is not the only aspect of quantum technologies. So quantum technology has many aspects. So one important aspect is quantum sensing or quantum metrology. High precision measurement is done in this. So quantum radar is example. I will show some cartoons to elaborate some examples of quantum sensing, what can be done. In quantum computation, main task is to speed up. So if you can do something classically with, say, n square step, quantum mechanically, if I can do it with n steps or root n steps or log n steps, it is better. So, or you can do something with 100 steps. If I can do with a quantum resource with 10 steps, it is better. So the lesser number of steps means it looks less time. So, but how you make quantum computers? We make quantum computers with different kind of qubit. Optical, ion trap, NMR, superconducting. But in quantum communication, we always use the photonic qubit. So photons can be used for quantum communication and computation both, but NMR based qubit cannot be used for quantum communication. You cannot send a spin from here to America, but you can send a photon from here to America. Now, in quantum communication also there are two facets: security not needed, like teleportation protocol, and security not needed. So quantum key distribution I have already mentioned. There are quantum secret sharing. There are direct quantum communications where key is not generated, like quantum secure direct communication, deterministic secure quantum communication, etc. So there are many facets, but are they really isolated? The answer is no. There are tasks which requires the good things from both worlds. So quantum communication as well as quantum computation. So what kind of task? So for example, you think of a voting. So in the voting process, you have to keep the secret that who has voted whom. Whether I have voted BJP or I have voted Trinamool or I have voted Congress or I have voted CPIM, that should be secret. But at the end, it's a computational process. We have to count all the vote and find out the winner. So it's a computing which requires security, and multiple people provide into their input. So such things are called secure multi-party computation, and which has the aspects of both the world, computation and communications, and we have a very specific interest in secure multi-party computation task. Now, what leads to quantum supremacy or advantage? So it is the non-classical properties. So one such non-classical property is collapse on measurement. So let me explain. Suppose you have an electron and here is a nucleus. So This electron is in the ground state, we call it 0. It is in excited state, we call it 1. Classically, it is either in 0 or in 1. Quantum mechanically, it is simultaneously in both. But when you do a measurement, it will be found either in the ground state or in the excited state. You look at a photon, and here is a beam splitter. If the photon goes single photon, so it is simultaneously reflected and transmitted. So I repeat, it is not like that sometime it reflected, sometime it transmitted. It is simultaneously reflected and transmitted, and when I do measurement, it collapses to one of the detector. So if we just make this process, look at the top picture. So there are two detectors, either D0 will click or D1 will click. So this postulate is called collapse on measurement. There is no classical analog of it. So before that it was in superposition. Superposition is very much there in the classical world, but now this can be used for generation of a random number. So you send this beam splitter, if this D0 clicks, we call it 0. If D1 clicks, we call it 1. So we'll get a random sequence of 0 and 1. And Quantis is a random number generator sold by ID Quantic, and this uses this technology. So who buys it maximum? So different casinos buy it. Now you look at this. So a qubit is written as ket xi is equal to alpha ket h plus beta ket v, or in general alpha ket 0 plus beta ket 1, where mod alpha square plus mod beta square is equal to 1. So this is a single qubit state, which is superposition of two level systems 0 and 1. And if you do a measurement, it collapses either to 0 or to 1. So with which probability it collapses to ket 0? Mod alpha square. Which probability it collapses to mod 1? Mod beta square, and total probability must be equal to 1. So I assume these basics are done already in this FDP. And now for my convenience, I want to introduce tensor product. If you have a column matrix AB and another column matrix CD, you make a tensor product, then A multiplied to CD. So each term in the left is multiplied with the entire matrix in the right. So it becomes AC, AD, BC, BD. So now this qubit alpha 0 beta 1 can be written as a column matrix alpha beta. So in that sense, AB is a qubit, CD is a qubit, and this AC, AD, BC, BD is a 2 qubit system. So a single qubit system is a 2 cross 1 matrix. A 2 qubit system is a 4 cross 1 matrix. 3 qubit system will become 8 cross 1 matrix. So look at this. 0 is a matrix 1 0. Ket 1 is a matrix 0 1. So what is 0 1? So you do this tensor product and you get it. So now a n qubit system will be 2 to the power n cross 1. So with the increase in n, it will grow up so fast that classical systems will not be able to manage it. So what we will require? Will require a quantum system to simulate a quantum system. That was the logic understood by Feynman and leads to the idea of quantum computing. But for quantum computing, you need quantum gates. So what is a gate? Anything that maps uniquely an input state to an output state is called a gate. Now, our governing equation is Heisenberg equation. So Schrodinger equation. I write a time-dependent Schrodinger equation. H xi is equal to h bar del xi del t, and assume that h is time-independent. Then the JIIT is xi0. So xi0 is my initial state. This is JIIT, and what takes xi0 to xi t? E to the power I h t by h bar. So if you fix time and you fix the interaction Hamiltonian h, then every time xi0 will go to same xi2. So this is called a quantum gate. So a quantum gate means a fixed interaction Hamiltonian for fixed time, and it will always be expressed as a unitary gate. Now, if there is a state, combined state xi AB, which can be written as tensor product of xi xi b, then it is called separable, and if it cannot be, then it is called entanglement. Now, there are many gates, and each gate does a small computation. So, for example, x is equal to sigma x 0 1 1 0. So x takes 0 to 1, 1 to 0. This is a NOT gate. So what NOT gate does? It computes a function f of x is equal to x bar. So it's a small quantum computer. If you give 0, it will give you 1. If you give 1, it will give you 0. Now, there are other simple gates, since all other people have already spoken. I'm not explaining C0 gate, etc. But with this, what we do? With this, we make a smaller circuit. With some circuits, we make computer, and then we want to implement algorithm. So what kind of algorithm? And what is an algorithm? So algorithm is a systematic way to understand, solve a computational problem. So there are many kind of quantum algorithms. Okay. And what we are interested at the moment is variational quantum algorithm. We are interested in a quantum approximate optimization algorithm, which is a class of variational quantum algorithm, a subclass of it, variational quantum eigensolvers. But before we understand them, again recall that I mentioned that an algorithm is a systematic process for solving a computational problem. So who taught you the first algorithm? Primarily, our mothers taught us the first algorithm. So when I have been taught how to do addition, so my mother taught me that below unit place, write the unit place. So if there are two-digit number, 12 and 34, and you have to add. So 2 can write 4 below 2, write 3 below 1, and then 2 plus 4 is 6, 1 plus 3 is 4. So how many steps involve? 2 steps. If there are 3 digit, it will involve 3 steps. 4 digit involve 4 steps. N digit involve n steps. So this n digits, n is the size of the problem, and n steps required to solve is the complexity of the algorithm for solving this problem called summation. So it's of the order of n or linear in n. But now you look at it, multiplication. So 12 into 34, 12 plus 34 would require 2 steps, but 12 into 34 requires 4 into 2, 4 into 1, 3 into 2, 3 into 1, then 8 plus 0, 4 plus 6, 3 plus 1. So 7 steps are involved. So multiplication is more complex than addition. So in short, how we find out an algorithm's complexity, we just count that if the problem size increases, how the size number of steps increases. If it increases in polynomial of the problem size, we call it efficiently solvable. All such problems belong to a class called P. So these are the problems which you can solve easily. Now there are problems for which solution can be checked in polynomial time, but we don't know whether they can be solved in polynomial time. So all the problems which can be solved in polynomial time, their solution can also be checked in polynomial time. So P become a class of NP, which is non-reducible to polynomial. So there are problems in NP which cannot be solved in polynomial steps. At least at the moment, I don't know any algorithm. So we fetch such problems and develop cryptography, and then those cryptographic schemes are like RSA, Diffie-Hellman. So the background problems are this odd biprime factorization, discrete logarithm, and if you can make a computer fast enough, you may be able to solve them with a higher speed. But since it is non-polynomial, so we can increase the size of the problem and still protect it. Now comes quantum algorithms. So they belong to a class called BQP, bounded error quantum polynomial. So they can solve the problems with some error. So we know when it fails and when it passes, and we can also bound the error that 100%, say 5% of the time it will fail, 1% of the time will fail. Accordingly, I have to increase the iteration. We will use quantum resources, so it will solve some problems approximately in the polynomial time. And of course, all the problems that classically can be solved in polynomial time become a subclass, and this class is BQP. Now there are problems outside BQP which is in NP, and if you can fetch those problems and design a new scheme for cryptographic schemes, they will be called PQC, post quantum cryptography. So what is post quantum? A situation where a scalable quantum computer is built. So today it is not built. So even RSA, which is within the BQP, is still safe because there is no quantum computer which can break a reasonably big size RSA code. But even tomorrow, when a scalable quantum computer is built, PQC schemes can be safe. They are classical, they are still conditionally secure, but they can be safe. But then there are several conjectures in this. So conjectures in the sense that we are assuming that quantum computers can solve only BQP problem. We are assuming that P is a subclass of NP. We are assuming that there are problems in NP which is outside BQP, and all these are conjecture. There is no proof. But at the moment, it makes sense to move for PQC in every security patch. So now in a cartoon, we are showing that in a classical bank, everybody is closing their account and everybody is opening their account in quantum bank. And this girl asked him, and then he showed that yesterday a scalable quantum computer is built, and so RSA is no more secure. So it will not happen on a day. Suddenly on one night, it will not happen like a Spielberg movie. But in a post-quantum world, definitely you have to move from this kind of banking to a more secure banking, either using PQC or using quantum cryptography. Now, I showed you that I'll talk to you something about sensing, etc. So this is the famous Galileo experiment, Galileo holding a ball and throwing it. So same thing, who wants a hand to throw the ball? So I can hold an atom with 2 light and drop it, and then send some pulses, and looking at the interferometer, I can detect how much time this ball required to fall down. So classically, I can measure G as 9.81, 9.82, etc. Or 3 digit, 4 digit. Quantum mechanically, I can measure up to 10, 12 digits. So 10th, 12 digits give me a very good sensitivity and what kind of differences. So look at it. So this is a modern prospector. So all these European countries are rich because many people went for adventures to India or Africa and many places look for gold, coal, etc. below the ground. So modern prospectors can go with a quantum gravimeter. So there is a company which link you can see. They have done scan the landscape of Odisha where we already know what is inside. And if there is a iron in one place more, manganese in one place more, then the gravitational acceleration at that place will change 10, 12, 14 digits. And locating that from the known models, they make a use machine learning and train their systems to detect or give a potential contour map of what is inside the surface. So the machine shows a gravimeter that this kind of surface structure below the surface structure. So you can decide where to dig, where to look for manganese, where to look for calcium, etc. So a modern prospector can use that. Not only that, if you have, suppose some terrorists have created a hole below the parliament and you have a gravimeter, so this reduction of mass will cause a very, 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 very small change in the gravitational acceleration and you can detect it. Now you look at this. So this is a handheld MRI. So handheld MRI is maybe possible in near future using a quantum sensor. So many things will be impacted. How will you all in quantum computers? I have already mentioned there are many different options to go for. So I'm interested in photonic quantum computer, but every time you see this kind of Sundar Pichai is standing, this kind of quantum computer, which is very big. So, but this big part is not used for computation, they use for cooling. So most of the quantum computers, superconducting quantum computer, ion trap, etc. are very cool. But photonic quantum computer are not cool. Photonic quantum computer can work in room temperature. So each system has its own advantage and disadvantage. So here we show that a photonic quantum computer. We have a project in National Quantum Mission in which we are supposed to build a 48 qubit photonic quantum computer. It works in the room temperature. So you see 300 Kelvin, and superconducting quantum computer works at very low temperature. So here we show 0.01 Kelvin or so. So I skip this. So to elaborate the idea of algorithm, I would like to mention that the complexity I mentioned, we calculate the worst case scenario, not the best case scenario. And there are possibilities because I don't believe much on the present conjecture. So present conjectures are that PQC will be safe even when scalable quantum computer is built. It may be that those problems are not studied properly, and tomorrow, because you cannot prove that there will not be any polynomial solution of lattice-based cryptographic systems. So they are the best one in PQC. So here is a cartoon in which a student got a F grade in exam, and when teacher asked, he told that all the problems were in NP and they cannot be solved in 1 hour of exam. So I could not solve anything and I got a F grade. And the teacher said that if you don't study well, everything will appear in NP. So same is the question here. Have we done enough study to conclude that quantum computer will only be able to solve PQP, or there is a problem in PQC at the moment, the problem leading to PQC at the moment, it will not be solvable with the quantum world, and even you cannot prove that it cannot be solvable in classical world. So PQC does not require any hardware. So at the moment PQC is very it's a software level change, and it makes sense to move for PQC. But for very strategic communication, we should go for best possible quantum cryptography only. Sorry. Now, Lob Grover is an encouraging person. He was an Indian. He is an Indian. He graduated from Delhi IIT and he was born and brought up at IIT Roorkee. So Lob has a protocol for unsorted database search. So to understand unsorted database search, you can think of a telephone directory which is organized as per name, and then I give you a number and ask you to find out the name for that number. So it's not organized by name, and there are n entry. So you may find out in one trial, you may find out in 100 trial. So on an average, it requires n trial or n by 2 of the order of n. If the n is million, you need of the order of million trial. Now teacher asked the student that how many searches you need. He told only once. I'll call him and ask his number. But this is the best case scenario. So we don't calculate algorithmic complexity in the best case scenario, we do it in the worst case scenario. And we design different algorithms, quantum hybrid, assisted, etc. My talk is not on quantum computing, so I don't want to go deep into it, but I want to tell, unless a quantum computer is built, unless quantum computer is developed, quantum cryptography is pretty well developed. The solutions are already available, but unless quantum computer is built in such a way that classical cryptography is really in threat, people will not replace. And unless people replace, the market will remain small. And when the market is small, cost will remain high, and quantum cryptography will not be used in daily life. But PQC is a software level change. So in case of PQC, this is not applicable. So I've already mentioned that what kind of algorithms we can do, which algorithms are of interest. And we look at different other algorithms also, variational quantum algorithms. We are interested in distributed quantum algorithms, and on and off we work on those things. But since it's a FDP, so I have a Marion message for faculty members that I showed one slide, but I did not describe in detail, that where Peter Shore is asking a question that why are there only a few quantum algorithms? Why are not that many? So in few years back, till IBM introduced his free quantum computers, now we have free quantum computers from Huafu and many other people, and some Indian quantum computers will also be available soon in the cloud. So much before that, Peter Shore wrote that, well, we live in a classical world, we think classically, and we don't have a quantum computer to play and by making error, by trial and error, learn new things. But now you have many quantum computers, you can by trial and error learn new things. And when you want to teach a course, you want to make your students familiar to things, you can use this platform by our collaborator CDAC Bangalore. So they made some platform called Q inverse. So you write universe and replace U by Q and then dot in. And here are different algorithms, their circuits are inbuilt, they are a very nice video file. So this is an excellent teaching and learning tool. So I recommend strongly for FDP to look for Q inverse. Now, earlier I told you that there is a beam split and a photon come, here is a detector, here is a detector, and the detector clicks randomly. So classically, there is no such random things, because here the randomness is coming from the theory that it collapses randomly in one of the possibilities. Classically, there is no such thing. Classically, if you toss a coin and you did not know the outcome, that's because you did not calculate how much pressure you give, which side was up, how much was the air drag, and what was the gravitational acceleration there. So if you know all these things, you need to solve Newton's equation and you will know what will be the output. Quantum mechanically, it's not like that. The theory itself is random. So a photon comes. Now, the detector experiment, you can tell that, well, half of the time detect light goes here, half the time it goes here. So just like I have a say this key, and I'm throwing a ball. The ball may go this side or this side. So, but it does not go in both sides. But how do we see that it goes to both sides as I described? So light comes 0, it gets in superposition in both sides with half probability in the same side, half probability reflected. Then there are mirrors, and now you see here it's always click, here it never click. So when ever click means here constructive interference happen, here the destructive interference happens. But it was a ball that you send 100 ball, 50 goes here, 50 goes here. So out of the top 50, 25 would have gone here, 25 would have gone here. From the bottom 50, 25 should come here, 25. So both the detectors should have clicked. But here we see that only this detector is clicking. This is called Mach-Zehnder interference. Now all these elements are beam splitter, a mirror, these are quantum gates for me. So a state 1 by root 2 0 plus 1 by root 2 1 is a plus state. So I can write this as a matrix. A beam splitter can be written as this matrix. And then you can write the Mach-Zehnder interferometer as a circuit. So this is nothing but a quantum circuit. It's a photonic circuit. So I'm putting some time in this because we are interested in photonic quantum computing. So this is a photonic quantum computing with hyper entangled states, and here the phase is controlled by a very sequential quarter wave plate, half wave plate, quarter wave plate. It's not very difficult to understand. So NOT gates are implemented. How NOT gate is implemented? You see that. So these are the angle of optic axis. So different optic axis can implement different things. And how is your visualization of the quantum computer? A laser came, it goes to a nonlinear optical crystal, creates a so at the moment we are using PPKTP. It creates entanglement. Part of the entangle goes in top, part of the entanglements come down, and then from this entangled states. So I have two photons which are entangled. So, but there are more degrees of freedom in an entanglement. So I use polarization degree of freedom as well as a spatial degree of freedom. And then from each photon we have 3 qubits, and this is a 6 qubit system. So this is a 6 qubit photonic quantum computer which is available at IISc. And these things are becoming so popular. Now it's a Marvel's comic, and in Marvel comic, this character is saying a quantum particle does not exist in any one state, but in all of its possible states at once. And so you show that in collapse measurement, in a random number generation, etc. We are talking about this only, and even the Marvel comic is talking about that. Now, why do you need this thing? So if you look at SBI and click here, SBI website, then more information, you will see that there is a security patch. The security patch is TLS, which is a handshake protocol, elliptic curve Diffie-Hellman, RSA, etc. So SHA-256 is a hash function. So elliptic curve Diffie-Hellman, RSA, elliptic curve is one scheme. This is a composition combined scheme of Diffie-Hellman. So Diffie-Hellman background problem is discrete logarithm. So all this RSA, Diffie-Hellman, elliptic curve, we have BQP class quantum algorithm. So polynomial time with quantum algorithm, we can solve this. So that means if a scalable quantum computer is made, this will be vulnerable. But why at the moment it is not vulnerable? Because we don't have very large quantum computer. Now, coming back to then what is the solution? One solution is to fetch a problem outside BQP and in NP and develop a classical cryptographic scheme called post-quantum cryptography, or you look for quantum cryptography. So a simple algorithm for quantum cryptography is called BB84 protocol. In BB84 protocol, Alice sends a random sequence of 0, 1, plus, minus. So what is 0? Horizontally polarized light. What is 1? Vertically polarized light. So you have a laser sources and there are polarizer in front of that. Anti-diagonal is plus, say minus, diagonal is plus. So you send all this mix, and now you see here is a beam splitter. So just like random number generator, it will send in the reflected plus or transmitted part. In the transmitted part, there is a box of this color. This is called PBS. So polarizing beam splitter is an optical device which allows horizontal photon to pass and vertical photon to reflect. So if this detector clicks, it's called horizontal. Detector is clicks, so the state is horizontal. This is vertical. So in the transmitted side, we are doing a measurement in vertical horizontal basis or 0, 1 basis. What we are doing in the other side, transmit reflected side, I'm putting a wave plate which rotates the angle of polarization by 45 degrees. So what was initially polarized in 45 degree, if it is clockwise rotation, it will become horizontal, and this detector will click the transmitted detector. Otherwise, the 135 degree polarization will cross to click of this reflected detector. So we can do randomly measurement 0, 1 or plus minus basis. Once the measurement is done, Bob declares that which qubit is measured in which basis. The first one is measured in 0, 1, second one is also in 0, 1, third, fifth, sixth are in plus, and so on, but did not disclose the result. Alice tells that in which cases her preparation basis and Bob's measurement basis are same. So in those are the states to be kept. So in those cases, it is expected that the result will match. And now, so if I start with 1000, 500 is gone because basis mismatch. So for rest of the 500, 250 cases, Bob will disclose the result, and Alice will check that this result matches with the Alice's initial state or not. So if it all matches, there is no eavesdropper. If they don't match, in some cases, they find out the quantum bit error rate. So if the quantum bit error rate is less than a limit, then it is possible to do error correction, privacy amplification, etc., and use it. And if not, we discard this process. Now the beauty is, you see, where from the security is coming. If there is a Eve, and Eve does a measurement, and Eve measure a plus state, which is 1 by root 2 0 plus 1 by root 2 1, or 45 degree polarized, with half probability he will get horizontal, half probability he will get vertical. Now he got horizontal and he sent the horizontal state. But if Bob is keeping, means Bob has also done the measurement in plus minus basis. So a 45 degree, so a horizontally polarized light with half probability will appear as plus, half probability as minus. So half of the half times it will require an erroneous result. So 25% of the time it will show error. So any eavesdropping effort leaves a detectable trace. Why if cannot wait for basis disclosure and then do a measurement? Because then he has to copy the state, but no cloning theorem does not allow it to do that. So no cloning theorem, Heisenberg uncertainty principle, collapse on measurement, etc. are leading to the security. It's not conditioned on the efficiency of somebody else's computer, computational power, etc. So this is unconditionally secure. Now, with all these things, we can make, with a random number generator, we can make our casinos fair. Casino owners will also feel safe. The lottery boards that each ticket can be equally probable. We can design quantum option schemes, quantum betting schemes, and claim that our country is corruption free, our voting is unquestionable, etc. But why we cannot do all these things now? So this cartoon explains that. So teleportation is a scheme where a state, the information about the state disappears from one place and it reappears at the other place. It happens. This guy goes to a teleportation station. It's a very big imagination. So at the moment, we can only send some photonic states or states of electron only. And he reaches New York. And here, your ear and nose has been changed. And then the question is, she asks a question to the teleportation hostess that what happened. And the teleportation hostess tells that, well, because of the noise, we could not reach the unit fidelity. Fidelity is a measure of how good is the copy. So this is a big problem. So there are, we talk about BB84 protocol. There are several other protocols. What I do in my lab is called coherent one-way protocol. So we have coherent one-way protocol, DPS protocol, etc. So there is a particular kind of attack called PNS. So these protocols are relatively more strong against photon number splitting attack. And we implemented coherent cow protocol in our lab, and for different distances, 40 kilometer, 80 kilometer, 120 kilometer. And we have shown some graphs with different kind of things. So dt is dead time. So a detector, single photon detectors, one detects a photon, then it creates an avalanche. So 1 to 2 electrons, 2 electron to 4 electron, 4 electron to 18 electrons, and so on. So 4 to 8, 8 to 16. So it continues. So our avalanche happens. But at the time when this avalanche is happening, if another photon comes, it cannot be detected. So the detector is dead or insensitive for this time. So this is called detector dead time. So if the dead time increases, so you will be able to detect less photons. So naturally your key rate will come down. So it is showing that how key rate changes with the detector dead time. Then there are compression ratios. So I told you that we do privacy amplification, error correction, etc. So most cases for error correction, I do something called LDPC. So when I implement LDPC, I have to choose a compression ratio, and if the compression ratio is depend on compression ratio, that how much, what will be the key rate. Similarly, there is a disclose rate DR. So how many results Bob are disclosing to find out the existence of E. If you disclose less photon, then your key rate will be higher, but confidence on the accuracy or secrecy of your key will be reduced. So there is a trade-off. Now these are the setups which we receive from a DRDO lab. We will not disclose the name, etc. for testing in our lab. So we have an environment chamber where we can create temperature and humidity as I need, and we put a spool of fiber of 80 kilometer length inside and look at that how quantum bit error rate varies with time, how secure key rate varies with time, and you can see that secure key rate is more or less same for a long time. Then we change the temperature, and with all the temperature, so this gives a practical test that when we take things outside the lab, how it will behave. So the plots are self-explanatory. I'm not describing much. I'm just moving for that with the humidity or things like temperature does not have much effect. And then there are, in the beginning I told you that this is a field which is open for everybody. So in the lab I need FPGA, so I need electronics people to help me in FPGA handling. I need people for computer science. I need people from applied mathematics. I need people from physics. Means everybody has a problem to do here, and it's very interdisciplinary. And even in the starting, I told that poets were also interested. So one very interesting problem is finite key analysis. So security proofs are always interesting, but security proofs which are provided today are for asymptotically large key size. But in reality, when I make a key in the lab, they are finite in size. So whether that impacts security, the answer is yes. And it has a very big relevance here. So for cow protocol, we did it for the setup which we have shown. So we put all the realistic parameters like how much is my detector efficiency, how much is the dart count, etc. And then we find that our cow protocol for optical fiber of 0.2 dB loss per kilometer is secure only after 180 kilometer. Does it mean at 190 kilometer we will not get a key rate? Definitely we will get a key rate. But that key, we are not confident about security of that key. This finite key analysis allows me with the practical parameter that up to which distance the key is secure. Now there are some experiments in Lakshadweep which made much noise. So one needs to check that whether it is secure or not for such a distance. So differential phase shift QKD is another version of the differential phase reference QKD. We work on DPS also. So these are our lab, and we have done the similar exercise, and here the distance is relatively lower. Now, one of the big problem of doing a large distance fiber optic based quantum cryptography is that, just like I show that this can work up to 180 kilometer or so, there is a loss issue. The best thing which you can do, unless you use a satellite, is twin field QKD, twin field quantum cryptography, or twin field. So for that you need a very, very good quality phase stabilization. So Shubhadeep, I don't know he spoke in this FDP or not. Shubhadeep is in Ayuka, Pune. So Shubhadeep's team developed a very nice phase stabilization technique, and we added the cryptographic aspect to that, and we showed that. So we are in many newspapers. We showed that the TF-QKD, twin field QKD, can be done with this, and then we can have a repeat. We can achieve very large distance without a repeater. These quantum repeaters are not available, so it was in much news. But TF-QKD now DRDO is also interested to do. Now, the question is, will your money remain safe if bank starts using BB84? I don't know. So unconditional security does not mean unhackability. So we have already explained, given you an idea of optics, which can be used for BB84 implementation. Now I send a if, a horizontally polarized light, and it comes here, and you see, sorry, vertically polarized light. So from Malus law, there is a polarizer which is a vertical polarizer. 100% of the light goes to LD4, but no light goes to LD3. So LD3's temperature does not change, wavelength remains same, but so already it was L lambda 1, so H is in lambda 1. But vertical absorb 100% photon and become much change and lambda 3. In these two cases, from Malus law, 50% light goes. So what I am saying that you still cannot do a simultaneous measurement in 0, 1 and plus minus basis. But you can measure the wavelength, and from wavelength you can determine which one is what. So you can attack. But now how to stop it? So here is a C, and C is called circulator. So if send a light, so there are 3 ports. So if it comes from 1, it goes to 2. If light comes from 2, it goes to 3. If it comes from 3, it goes to 1. So now I can put a circulator in LSS port and stop this kind of attack. So this continuous thing between two parties is still there. So I mentioned that I'll talk about other hacking system. So I mentioned that there is a beam splitter and the light come and it goes to port 1 and port 2 50 times. And then only Bob is, say, in BB84, the Bob's measurement on 0, 1 and plus minus basis is random. But if this beam splitter, every optics is wavelength specific. So the 50-50 beam splitter, which is a 50-50 beam splitter, 1550 nanometer or say 800 nanometer, is not 1550, another wavelength. So you see that with the wavelength, how it is changing. So in some point, for a particular wavelength, 100% light will go in one direction. So if you can change the wavelength of the light coming, then it will not be equally probable to be measured in 0, 1 and plus minus basis. And this biasness can be used for hacking. Similarly, you need all these keys to be equally probable, as many zeros, that many one. Then only somebody will not be able to guess the key. But the detector's efficiency eta 0 is not same for every time. So there is a time variation. So only if both comes here, then both the detectors are equally efficient. Even the commercially created detectors are not never equally efficient. Now you can make a time lag and make that eta 0 is much more efficient than eta 1. So then you can guess that most of the time the key will be 0, not 1. So these kind of things are there. Now there is a Trojan horse attack. So most of you are familiar with the Trojan horse attack. It's an innocent pulse sent somewhere. And so here is a Alice's code, and there is a laser. Here is a circulator, and it goes in the Alice's code. It reflects from all the components, and from that we get some kind of information how to extract. And we look at, there is a laser has a 2 reference point which comes directly to the detection schemes, and one goes, and then comparing that I know some information about Alice's activities and things. So how to stop it? Once again, you have to put a circulator in Alice's code. So here is a cartoon. Alice and Bob are boyfriend and girlfriend. Bob is very demanding, and Bob told Alice that, well, I don't trust you. Alice says, why? Because you reflect light. So Alice says that that's why you can see my beautiful face. But Bob tells that then that others can also see your face. So this is the Trojan horse attack, and Alice told that then give me a circulator. Now, as I told in the beginning, in a post-quantum world, the life will change like anything. So life of not only cryptographers, cryptologists like us will change, it will change to common people, somebody working in a police station, somebody working in CBI. Because if I show you that how to take care of the Alice's thing. So all the exploitations which I have shown in hacking are exploiting device imperfection, but we have something called device independent QKT, not very feasible at the moment, but we can have measurement device independent QKT. But tomorrow, if I have a device independent QKT, then there is no, even the device imperfection will not cause any leakage. The service provider does not have a copy. So all this digital forensic, what is done today, to find out that which message I have sent him, what I spoke with you in a call, there will not be any record. This will be absolutely secure. So pollution will also change. The job of a police, job of a CID officer, job of a CBI officer, all will change. That's what we want to show in this cartoon. Now, where are the weaknesses? So one weakness is in authentication. So key distribution, before the key distribution, Alice and Bob must know that they are talking to each other. And identity authentication used today is usually classical, even from the beginning of BB84 protocol. So lately we have designed several protocols for quantum identity authentication, but there is still, it's not fully quantum. A cryptographic protocol cannot be fully quantum. For identity authentication, some kind of tokens, some OTP has to be kept, and it will be classical. Then there are many ways to look at the protocol. So one QSDC protocol, a quantum secure direct protocol, is DL04. Without going into much detail, because my time is finishing, there is another speaker. I quickly tell you that you can visualize a cryptographic scheme as a game in which Alice and Bob is trying to increase their mutual information, and Eve is trying to increase our mutual information. So this is a non-cooperative game, and you can look at it from the game theory perspective and use Nash equilibrium to finding game theoretic security bound on quantum bit error rate, which we did in a recent work. And this is a gaming the quantum. So there are two kind of things, quantum. So one is called quantize the game. So there is a game which you are, and there is a game in the quantum. So a quantum mechanical scenario can be viewed like a game, and then there is an existing scenario you want to see it like a quantum with the quantum resources. So that's the difference between quantized game and gaming the quantum. Now there is another aspect which we have briefly touched in context of auction, voting, etc., which is called secure multi-party computation. So think of a function f of ij, it has to be computed. So I'm interested whether I is equal to j or I is not equal to j. So if I is equal to j, f of ij is equal to 1, and else it is 0. So I want to compute a function, and the person who will compute this function will not know the value of ij. He will not be able to conclude anything other than the function concludes. That is, so this is called quantum private comparison. This has many names. Socialist millionaire problem, where there are two millionaires. They want to compare, they have equal assets or not. There are other tasks like quantum e-commerce, quantum veto, quantum voting, quantum lottery, quantum auction, and we work on them. So these are different aspects of quantum cryptography. So quantum cryptography is not restricted to QKD. And then lately, just last week we posted this, 26 June we posted this last week in archive, a generic structure of the protocols for quantum auction and quantum summation and their relation. So I would like to note that this Kabir Chandru is a second year. He just finished second year and moved to third year. Undergraduate student, and the undergraduates, Professor Panigrai and I both enjoy working with undergrads, encouraging them, and undergrads can do very good work in this field. So since there are many faculty, it's a faculty development program. I encourage you to look at that possibility, encourage your undergrads, get things done with the undergrads. Then, so far I'm talking about BB84, fiber-based cryptography. So how to increase the distance of optical fiber by using TFQKD, that needs stabilization. But even with the TFQKD, I can do something like 1000 kilometer, 1200 kilometer of repeaterless quantum cryptography. But if I want a more distance, then we have to do satellite assisted quantum cryptography. So satellite will work like a trusted node. So, but say satellite is above Delhi and created a key, and then satellite is above Kolkata and then create a key, and then it declares the key Delhi XOR key Kolkata, and Kolkata XORs his key Kolkata, then both of them have called key D. But to generate this, we have to separate the pulses, and then there are environmental impact. So we often send say circular light, but light with the circular cross sections, but the beam which reaches the satellite become elliptical. So we do some mathematical modeling with elliptical curve approximations, but we don't have enough time to discuss them. And then the final thing is so we saw that game theory as applications, environmental modeling and applications. So there are different aspects of cryptography. So final thing is I talk about graph theory. So every protocol of quantum network can be seen like a graph. And let's not talk much. We are still not in a post-quantum world. So a few days back, I was talking in IIT, IIEST Shibpur, and I made the slides that today in QKD shop, we have superconducting nanowire single photon detector. They're the best single photon detector, but still they are not most efficient for 1550 nanometer. In optical fiber work with 1550 nanometer. Quantis is a random number generator. Clavis-3 is a cryptographic solution. Payload for satellites is available, but many things are not available. Some of these will be available in near future, and the world will change. But certain things which are not allowed by physics, will not be available even in far future. So, for example, perfect quantum cloning machines will never be built. Quantum broadcasting will never be built because they violate quantum mechanics. So, once again, with the carry-on message, I will stop. So far, the schemes which I described are primarily discrete variable schemes for quantum cryptography. So there is a continuous variable schemes also, and I mentioned about the direct secure quantum communication. So one of the undergrad, Shikara, did a project with us. He was from ISAR Pune, and we wrote a protocol of continuous variable direct secure quantum communication, which was experimentally realized by Paris and Zapata, a group in Italy. So that's the only, or I should say that was the first scheme of CBDSQC which has been experimentally realized, and they referred to it as a Shikara protocol. And who is Shikara? Shikara was an undergraduate student at that time. So the carry-on message for faculty is that it requires crazy, bright ideas undergrads can do. It does not require a very deep sense of quantum mechanics to start with. So encourage your students, teach minor degree courses, teach different courses, work with it. Let there be more minds to put into it and get new results. And before closing, we want to mention that we are looking for different kind of things like MSc Physics is open, and our MSc Physics students can also take, so those who have finished BSc, MSc Physics students can take different courses on quantum information, optical and quantum computing, etc. And many of them are being absorbed immediately after MSc to CDAC, CDOT, and such other organizations, even the startups in Delhi. And for PhD also, we were open. But then this one is closed now. We were till last Friday, we were organizing a workshop called Opportunities in Quantum Technology. So yesterday, L. Venkat Subramaniam, who was formerly heading IBM, spoke, and I just shared in LinkedIn, etc., the YouTube link that why somebody will do quantum technology, what are the prospects in India. And we have a MTech program also. So if you have students, since it's a faculty development program who may be interested, especially undergrads, there is a fellowship of 15,000 rupees per month also. So you can share with your students and just take a screenshot that we are looking for bright minds to develop the goals of national quantum missions, and we need hands who can repair things, who can develop technology, and many problems are technological, and there is options for everyone, means whether it's a BTech in electronics, BTech in computer science, or anything like that. And here are suggestions of some books for beginners, and of course Nielsen Chuang is the book for advanced readers. And if there are people who speak and read Bengali, I highly recommend the new Bengali books on quantum information by Professor Guru Prasad Kaur and his students. It's a nicely written book. So you can start with some early book and then move to Nielsen Chuang or some books. Press skills notes are also very good. So my time is also over, so I'll stop here.
Thank you, Professor Pathak. I can say that for someone who is not familiar with this topic, I thoroughly enjoyed your talk because there are also a lot of things which I learned from this. We just have 1 minute left, so if there's time for a quick question by any member of the audience.
I have one question. So, can you hear me?
Yes.
Thank you. Yeah, thank you for a very interesting and informative talk. I guess you have discussed fiber-based quantum cryptography, but on the, I think, atmospheric slide, you have also discussed quantum cryptography. My question is, do you need Gaussian or non-Gaussian states in your experiments? And also, any thoughts about how to minimize diffraction and losses, and what states are better for those ones to reduce these impacts on the state?
There is no straightforward answer, but wherever things works in Gaussian states, means if you can do the same task, so far the experience is that if you can do it with the Gaussian states, it's much easier to do it with Gaussian states. And we have done several theoretical schemes where we use non-Gaussian states, especially for continuous variable CVQKT systems. Like we used squeezed two-mode squeezed states, but in general those are theoretical works of ours. In the lab, what we have is a simple laser source which is Gaussians, and in the lab whatever we do is fiber optics. We do some free space things, but that's only tabletop. And experience of handling non-Gaussian states are restricted to theoretical work, but if there is a task in which you can do the task both with Gaussian states and non-Gaussian states, my usual bet without a quantitative measure is that to go for Gaussian states. That's experimentally much easier to handle.
So, if I understood correctly, Gaussian states for fiber optics, they are more robust to losses.
So make a comment in general like this. Means there are many aspects. Means which kind of encoding you are doing, and whether suppose you are doing a polarization encoding and your fiber is polarization sensitive or not. So there are too many facets. Means I don't want to make a very generic comment, but for free space things, say you want to make just take an example. So many people, and there are many protocols, including our protocols, which uses photon added coherent states, photon subtracted, photon added then subtracted coherent states. So these are engineered quantum states which are non-Gaussian. In contrast, many of these states do the tasks which can be done by simply a Poissonian state, which is a coherent state. And making any engineered quantum state is very difficult in the lab. So it's much easier to use a just the output of a laser,
Thank you.
maybe an attenuated output of the laser. And if the task, both the tasks can be done with the same thing, with the same resources, it's much easier to do with the coherent state. But
Thank you.
not to make any conclusions beyond what I made explicitly. Because without a quantitative measure, scientific comment should not be made.
Well,
Sir, one more question.
Very quick, because like we are.
Yeah. One more question. Actually, I miss a few parts of your talk. As you say, 0 and 1 are for horizontal and vertical. And what for plus minus? I just miss it.
But once again,
Am I audible, sir?
yes, 0 and 1.
0 1 is for polarization, vertical polarization and horizontal polarization. Am I correct?
Yes.
But what for plus minus? You are talking about
45-degree and diagonal and anti-diagonal polarization.
Okay, diagonal and why
So
3
a
is
diagonally
coming to the
polarized
picture?
state, a diagonally polarized state, if you move to a polarizing beam splitter and put two detectors, with half probability it will be horizontal, half probability it will be 45 degree. Similarly, if you have a vertical polarized state and you put in anti-diagonal diagonal basis, it will be with half
Sir,
probability.
I got it. But sometimes you told 3 for a spin 1 particle, there are 3 states 1, 0, -1. But for photonic 3 state, what are?
No, this diagonal I'll call plus, anti-diagonal I'll call minus.
Minus, okay. Thank you.
This is the name. The plus state means 1/√2, 0 plus 1/√2, 1 means 1/√2 horizontal plus 1/√2 vertical. And the other one is 1/√2 horizontal minus 1/√2 vertical.
Very good.